science like there's no tomorrow.
Welcome everyone after the break. This is part number 2 of the financial engineering course with special interest on interest rates and XVA. In the previous lecture, we have discussed the equilibrium and term structure models, and we also have covered the concept of the HJM framework. Today we will expand these topics. We will discuss the assumptions, arbitrage free assumptions of the HJM model, and also we will go into some details regarding some particular choices, so like a Oosterlee model and a full-white model. Those are the special cases of the generic HJM framework. Let's take a look at the content of today's lecture. So we start with the arbitrage free conditions under HJM. So this will it's a key point of the HJM framework where we actually specify what is the main driver for any interest rate model which belongs to the Hit-Jaron-Merton framework. Then we go through 2 models. So of course, the models discussed here are just the special cases. As you can see, every interest rate model which belongs to term structure models, it belongs to the HJM framework, so you can choose it yourself, you can derive those models yourself. But today I will concentrate only on the Oosterlee and the full-white models. We will perform a number of Monte Carlo simulations, and I will illustrate you the whole idea of behind the term structure models, which is that if we use the term structure model and we simulate Monte Carlo paths, we can always recover fully the yield curve. So the yield curve is an input to the model, which is contrary to the equilibrium models, where the yield curve will be an output. So in that case, we would always need to recalibrate the model. In term structure models, the yield curve is always well preserved. And that's the key point of the whole HJM framework. We will wrap up this lecture with the summary of the most important elements discussed in this lecture, and also a homework. I have prepared for today 3 exercises that I think that you will find quite insightful and useful. We will be talking about the simulation and also some kind of hedging experiment that will be performed. Enjoy the course. Now let us wrap up what we have seen so far about HJM framework. First, a very important element was that the short rate is related to the instantaneous forward rate, and the relation is as follows. So the short rate is defined as the limit of the instantaneous forward rate. This is very important takeaway. The zero coupon bond, so the bond which will pay us 1 at the maturity time t, with the maturity t, is defined as follows. So we have a money savings account today, so this is typically equal to 1. But for convention, I always prefer to have it included. This is typically helpful once we talk about the measure changes, and nicely MT will cancel out. Then we have an expectation under the risk neutral measure 1, because this is a payoff at the maturity, so we discount today. And then we have a discounting with the money savings account 1 over MT. If we just substitute the definition for the money savings account, we have an exponential function here, exponent of minus integral from t to t rs ds times 1, which is the payoff. And here, of course, this rs, it is related to the instantaneous forward rate with this relation. Okay, so now what we have to do, we have to find our dynamics for the instantaneous forward rate. And of course, we will follow the same strategy as we have seen already in the previous lecture. We define tradable assets, and we make sure then that those quantities, so the tradable assets over some numeraires, so certain portfolio of assets we have, divided by numeraire, that this is our numeraire in our measure, that quantities need to be martingales. So of course, once we talk about the risk neutral measure, this means that every asset in our portfolio, in our market that we're currently working with, has to be martingale. Every asset divided by the numeraire has to be a martingale. So this is the important step to derive those parameters as alpha and of course sigma. So okay, the relation between instantaneous forward rate and zero coupon bond is as follows. And we can also find the following relation. So if we take an exponent and then just reorder this equation, we see that the zero coupon bond also is related. It can be expressed as the in terms of instantaneous forward rate, which is minus integral from t to t FTS ds. So you see, this is slightly different definition what we have seen before, because before this zero coupon bond was expectation, and then we have minus integral from t to t r s ds, and now this is, you see, this is equivalent. So this it's also, of course, because we observe it at today's term structure, so we integrate over maturity. So this is also, you have to be careful here. This first element tells us where we are in time. So it's actually, we are today. So we observe it from today's perspective. So only the maturity function changes. This means that this function is also deterministic because it's defined from the market. And how this is defined from the market is actually defined in this way. So if I give you discount bonds, or so-called zero coupon bonds from the market, you can construct today's instantaneous forward rate by simply differentiating the zero coupon bonds with respect to maturity. Of course, in practice, you see that there is we assume a partial differentiation. In practice, you would have only a few zero coupon bonds, let's say maybe 10 and 15. Then you have to make also sure that you impose some interpolation, that there is some continuity. Otherwise, this derivative can be very difficult to find. Okay, so what we have so far, we have defined market instruments. We have a money savings account. We have a zero coupon bond. So we have to impose now the arbitrage free condition. Of course, the arbitrage free condition is that every asset in our economy discounted with the money savings account needs to be a martingale. So we are looking at the zero coupon bond PTT divided by MT, which is the money savings account, and then we apply Ito's formula. Of course, in this case, Ito's formula is much more complicated because we are dealing with integrals, and also this our function has two arguments. Of course, it doesn't really matter that the capital T, or in this case S, doesn't really matter because it is what we are interested is the maturity T. But of course, Ito, it goes with respect to small time t. However, you see the small time t today's is also in the integral, so this means that the Ito derivative, it will be rather complicated. And so after substitution of all these terms for zero coupon bond and money savings account, we end up with the dynamics of this expression. Of course, this part is also, this is also FSS. So this is by the definition we have seen in the previous slide. So you see that we have an expression for this a ratio for the asset divided with the money savings account. It's an exponent, and then we have a function of instantaneous forward rates. And also we have two different integrals. The one integral corresponds to TT. So this integral corresponds to the zero coupon bond. And then we have also money savings account. So this is MT, which is integral from 0 to t rs. So we see that's slightly more advanced what we have seen so far. However, we know that this quantity, so this quantity here, needs to be a martingale. This means that if we have a process for FTS, and I think we have defined already earlier, so this was under this measure P, this has dynamics. So this dynamics will be used in that derivative. And of course, if we impose the arbitrage free conditions, then this alpha t, alpha p would need to be adjusted such that those zero coupon bonds divided by money savings account, the numeraire, are the martingales. So this is then defined as dzt. And we know this dzt because it's martingale, so this means that the drift has to be equal to 0. This is the output. So I didn't want to derive the Ito derivative for this expression as it is rather involved. I think you can find it in a book or in the literature, the details how to step by step find this derivative. That is not necessary actually to get the output. It's a little bit of maybe algebraic expressions, you have to really work it out. But at the end, you end up with the famous HJM lemma about arbitrage free conditions for the instantaneous forward rates. And the output is as follows. So under the arbitrage free conditions, under the risk neutral measure Q, the instantaneous forward rate is defined by alpha Q. Of course, we have sigma and here dWQ. And then the arbitrage free condition, the most important finding is that it's given in terms of sigma times the integral from t to t, sigma ts. So this basically means that our drift here, it's fully determined if we would like to be under the risk-neutral world, arbitrage-free world, then the drift is fully determined by the volatility. So this is very important finding, because this means that if we would like to model instantaneous forward rates, or we would like to model short rates, the element that we have to define is the volatility for the instantaneous forward rate. Once we define this volatility, then we know the dynamics for the instantaneous forward rate is arbitrage free. So this is very important, because this means that if somebody, for example, estimated this alpha, let's say from historical data, it doesn't really matter. It's only what matters is the volatility and uncertainty. I will leave the proof outside, like I just mentioned, from this lecture. However, it's a really nice derivations, especially if you like Ito, where you have also involvement of integrals. The next step, actually the final step, once we talk about the short rates, is to find out what is the dynamics of the short rate under the HJM framework. We have just derived the proof, or we have derived the arbitrage free conditions, which state that under the HJM framework, volatilities are the most important, as they define the arbitrage-free or risk-neutral dynamics for the instantaneous forward rates. Now we would like to find out, okay, so how this process for the short rate would be affected by that finding. So we have to go back now to the definition of the instantaneous forward rate and short rate. So this is of course, relation from the stochastic differential equations, the equation here. We can of course integrate, and we can set capital time t go to small time t, and if we integrate, then we get the dynamics for our short rate. So this is what happens here. So instantaneous forward rate from t to capital time t, there will be some the following, let's say, well-known Ito representation. So this is just the integral of the SDE. If we set capital T to be small time t, then short rate is given in this way. And of course, now what we need to do is to find the dynamics for the short rate, because we are talking about short stochastic differential equations for the short rate. If we would like to apply the Ito's lemma, we also have to take into account the Leibniz integral rule. So if we have the rule is written down here. If we have an integral which has limits as a function of parameter, let's say alpha, and then we would like to differentiate with parameter alpha, then there is a special rule how to integrate also the limits of that integral. After application of the Leibniz rule, the dynamics for the short rate is as follows. So we have a derivative of the instantaneous forward rate with respect to time. So you see that this zero here, this means that this curve is the curve of the maturity. It is deterministic. It will be derived in terms of zero coupon bond here. So if we have here zero, we have zero here. So those are zero coupon bonds as given from the yield curve of today. So we have just simply, this function is deterministic. There's nothing stochastic. Then we have alpha tt. So this alpha tt, it is function here. So alpha tt will be sigma tt, and then we have this integral tt. So that's basically zero, because then we just integrate over the from the same period of time t to small time t. So this integral has to be zero. Then we have integral from 0 to t derivative of alpha st ds, which is computed directly by substituting alpha q to this expression here. Then we have an integral over the partial derivative of the volatility with respect to Brownian motion. And then we have one more component corresponding to, also we have Brownian motion here. Here it's important maybe to keep in mind that this relation between S and T, it is this volatility function here, it's allowed to also be dependent on a different instantaneous forward rates. So if you look here, it is we will have a different drifts or different volatility structures for different maturity T. So if you have 20 zero coupon bonds and you like to derive 20 different processes for the instantaneous forward rates, then you have 20 different, let's say, parameterized volatilities. But in our case, if we talk about only short rates, then this capital T is equal to the small t. Then it will be just a function of the time t. There will be no dependence on the capital T because we are just dealing in a short rate setting. Okay, so then if we specify alpha, and then we specify sigma, then we have function alpha, we have to substitute and then compute all those ingredients to find the dynamics of the short rate given the arbitrage-free condition imposed from the HJM framework. We have learned so far that by specification of the volatility for the HJM framework, we can have we may generate many different short rate models. Let's check it how it works in practice. So the simplest possible volatility you can think of is, of course, to choose volatility to be constant. So we take sigma t, capital T, equal to sigma. And this is sigma t. Sigma tt is, of course, this volatility structure. So it's actually this volatility that we specify for the HJM. Of course, once we specify sigma to be constant, immediately we can calculate also what is the function for alpha under the HJM condition. So let's go back. So we specify sigma tt to be constant. That implies that our alpha under risk neutral measure is simply sigma squared t minus t. Of course, still very simple calculation. And then if we know these two elements, so we also know this and we know the sigma tt, we can generate or we can derive the dynamics for short rate given the specification for the sigma under the HJM framework. So what we have to do, we have to substitute our alpha. It will be a substitution here. We have a sigma substitution here. We have a sigma substitution here. And of course, we have a sigma here, which of course here will be, of course, 0 because t minus t is 0. And then we only have one left function. But this function, we already have seen it before, f0t is a function of a zero coupon bond. So it's minus derivative, partial derivative with respect to t of logarithm of p0t. And this function p0t, actually it is given as an input. So you have to specify what is your yield curve essentially, and you have to specify those zero coupon bonds. Then you plug it in to generate function f0t, and then you can have to substitute that into the dynamics of the short rate. This zero coupon bond curve, it is associated with a yield curve and is estimated typically is implied from the market instruments on what is the rate associated with a borrowing or lending over some period of time. So you can say that's one of the most important building blocks which is used in finance for interest rate derivatives. And like I mentioned before, this function p0t, it is has an exponential form, and you have to also impose some kind of interpolation between these points. So in practice, you may have a p0t1, p0t2, and so on. So of course, if you would like to calculate the derivative, you have to impose some kind of structure here. Later in this course, once we'll be talking about the construction of yield curve, essentially we will be building a curve, this curve, you can say this curve with some interpolation in between, and that will be based on market instruments. So we will go through the process of building a yield curve once we have number of swaps, some other interest rate derivatives, and then I will show you how to build the zero coupon bond. But for now, we can just consider that the zero coupon bond curve is given to you, and then you use this curve in order to simulate short rates. Okay, so after substitution, so many things will be just zero. This is those integrals and derivatives are trivial in a Oosterlee model because this is actually the name of the model which is associated with a constant sigma. So once you specify constant sigma, we arrive at the Oosterlee model. So after simplification, this is what we have. So we have a dynamics for the short rate, which is derivative of the instantaneous forward rate. So this is purely deterministic. We have volatility in the drift, and then we have, of course, volatility in the Brownian motion. After substitution, so we can just define new function theta, which is a function, deterministic function. Then we have a famous Oosterlee model with a time-dependent drift and sigma parameter. What is also very important and also interesting in this case is that because the model belongs to the affine form of affine class of processes, this is also discussed in the computational finance course, we can actually find the dynamics, or actually find the zero coupon bond function in an exponential form. So zero coupon bond is given by definition as an exponent of the expectation of an exponent, and we have a minus discounting here with a short rate, and that expectation, it is given in this form. It is a very, very powerful equation, because this basically means that if we have, for example, if we have time, let's say today is t0, we are t1, here we have a t2, and we are interested in a bond pt1, t2, and if we just apply this equation, so this will be T1 and T2, we will have, of course, this is still in the future. So this is already what we have discussed in lecture number 2. We will have one particular realization for bonds, because we have many the realizations here. So this bond obviously is a stochastic quantity, is not known today. So so if you have a path here, for every point here, we will need to perform a simulation of the nested Monte Carlo. So we would have to simulate all those short rates, and then we are actually able to get one entry of this conditional expectation. And then for the second path, we have to do exactly the same. So this is a nested Monte Carlo that we will need to simulate if we would like to get the zero coupon bond of time t1 to time t2. However, because the model belongs to the affine class of processes, and we have this solution, of course, later I will discuss exactly how to get those functions a and b, this is extremely interesting, because you see that this expression only depends on RT. So if we have a short rate model, this is time t1, time t2, we have a path which goes up to this moment. Essentially, this means that we can forget about this nested Monte Carlo simulation, because if we know the value of this is RT here, right? So if we have this value, we can just substitute the whole set of paths. So it's a distribution. We can get all those paths. It's a vector of paths. We can plug into this expression, and that will give us the zero coupon bond T1, T2. So you see, instead of calculating integral over all the paths from T to T, or T1 to T2, which we would need to do it here, we can simply get here, actually in our case will be RT1. So we just substitute the whole vector of paths, we just substitute this expression, and that would give us the definition, the zero coupon bond. So you see, extremely powerful machine, because now we don't need to do any nested Monte Carlo. We can forget about the conditional expectation, because we know explicitly the relation between short rates and also this expression. So this information about the transition density from T1 T2 is actually contained in deterministic functions A and B, which are actually known in closed form. So this is something that people often they don't really appreciate this expression, which is extremely powerful. And of course, later in this course, we will be talking about XVA in this relation that we don't need to do conditional simulation, so nested Monte Carlo. We can explicitly express, for example, swaps in terms of a path at a given point, given like we did here. It is crucial to gain computational power. So this is extremely important. Another way, for example, what we could also do is that instead of calculating those nested Monte Carlo paths, we could also do some kind of Longstaff-Schwarz algorithm, which essentially gives us the estimates of XT2 filtration here, let's say T1. We could also solve this expectations also, like here with a Longstaff-Schwarz LS model. This discussion about the simulation of using Longstaff-Schwarz algorithm, it's typically associated with pricing of indeed continuation values, conditional expectations, and that will be also discussed not in this course, but in a follow-up course. Once we'll be talking about the pricing of exotic derivatives. But here, I would say, this is the most important equation. And if you cannot represent your model in this form, if you cannot represent zero coupon bonds in this elegant way, and you always have to go via this conditional expectation, then your model will never be accepted as the market standard. So this is something to keep in mind, because as you can imagine here, we just substituted number of paths, the vector of paths, in order to get the zero coupon bond PT1, T2. Otherwise, for every path, we will need to do 10,000, let's say, simulations, which is extremely expensive, because that will need to be repeated for every sample from this distribution at time T1. So for every sample, you need to do Monte Carlo, nested Monte Carlo to get this integral, and then you can actually then substitute to get this zero coupon bond. So this is crucial, and this is extremely powerful tool. Let's perform now experiment, a Python experiment. The idea of this experiment is as follows. First, we specify some zero coupon bond curve. This curve, like I said before, typically will be associated with a yield curve, and you can estimate this will be typically an input to your model. This is in the exogenous models, it is always input to the model, but in equilibrium models, this will be the output. Yeah? So this is, if you have a yield curve, you use it in term structure models as the input. Okay, so we have the zero coupon bond curve. We take a Oosterlee model with some sigma parameter, and the objective is that we will simulate paths using Oosterlee model, and we will calculate zero coupon bond, but using paths. In this case, we are not looking actually for this nice representation. It is not important right now. Now what I would like to check is that if I calculate this integral, this expectation of e to minus integral, whether it will be equal to this input which I have. Because that's the whole assumption of those term structure models. That you have your yield curve, you use it in your model, you simulate your model, and you always get your yield curve back. And that should not change if I would change my parameter sigma. So this is the key element. Whatever parameter I would choose for sigma, the HJM framework requires or states that this zero coupon bond from model from simulated paths would be always the same as the ones that we have incorporated as the input of the yield. So that's you can also, this is maybe a little bit counterintuitive, because you could say, okay, well, if I change sigma and I always get my yield curve back, what is the point of having sigma? And actually, this is crucial in this framework, is that we choose sigma, we calibrate sigma using not the yield curve, but we calibrate sigma by calibrating the model to older derivatives, like, for example, swaptions, caps, floors, floorlets, whatever you choose. But you don't need to calibrate your sigma once we talk about zero coupon bonds yield curve as an input. So this is the key element here. Few small details. So in Oosterlee model, we can of course specify sigma, but we also have to specify R0. And R0 in the HJM, we already have seen it, is the instantaneous forward rate, and this of course here's 0, 0. So we have to calculate it from the market data, and then of course zero coupon bond. So P market 0, 0 is always equal to 1. So that's kind of useless, but you always have to make this epsilon far away, maybe from a rate for tomorrow or not for today. And then that will be estimate for our initial. Otherwise, this R0 would be always equal to 0. So that's not going to work. Okay, so objective is to take the input market data, so the yield curve, calculate yield curve from the model, and how this yield curve will look like from the model, and how this relates to the one from the market. This is a Python exercise. I already have put here results. So we have a yield curve as the market, yield curve from Monte Carlo simulation. Here we show the zero coupon bond. On x-axis, we have time to maturity. So this means if I would like to buy a bond 35 years from now, this means I will need to pay around 25 units, and then I'll have €1 in 35 years. Let's take a look at the Python code. Okay, so we start with a specification. Oh, here it's not good. Specification of the number of Monte Carlo paths. So this is 20,000. We have number of steps 250. We have a volatility 0.01. Here I have specified a yield curve. So this means we have a yield curve. It's a essentially very simple curve. I just specified we have a 4% for every maturity. This you can specify maybe more as you can choose different functions there, whatever you want. You can also do, for example, t squared, for example, then minus 0.01 t, or you can play with this function. You can try many different things. But for simplicity, I just take 0.04 times t. I choose 40 years as the time horizon. Then we generate paths. And in this function of generation paths, what I do here, first I estimate what is the R0. And this is R0, like I mentioned, I calculate at the small, let's say 0.01. So this is next day, let's say from today. So epsilon, which is close to today, as the input is a zero coupon bond curve. Then I calculate theta. So this is a theta we have seen in a Oosterlee model, which is the derivative of the instantaneous forward rate, and then we have a sigma squared times t. And then here we perform the Monte Carlo simulation. So we have a Oosterlee model. So we have a Euler discretization, theta times t times dt plus sigma, and then we have a Bernoulli motion. And then what I'm also doing, I'm storing here the discount factor. I'm storing this m, which is exponent of an interest rate, of the integral of the interest rate. And then I will take this money savings account. I'll take 1 over this m, and of course take an expected value of, and this will be 1 over m, because this will be our equivalent, the zero coupon bond. And I take these outputs m and r outside. So this is the output r and m, which will be later plotted. So you can see what I'm doing here. I'm taking zero coupon bonds. Of course, we have one zero coupon bond from the market, and then one from the model. It will be for every time step. So we have 250 time steps. I'm taking money savings account, take expectation 1 over money savings account, and then I'll plot those two curves. So let's run it. You see, it's nicely spot on. Sorry, let me just maybe show you. See, yes, let me take a look here. So maybe that was not very clear. So this is the part where I'm calculating the expectation over the 1 over mt, and here we generate the simulation. So let me run it again. And then you see there is an almost perfect match between Monte Carlo and market. What I will do now, I will change sigma. So for example, we have 0.01, I will do 0.02. Okay, now we see a little bit of volatility at the end, but that's related to the discretization of number of time steps. So let me do 500 time steps, for example, and then 25,000 Monte Carlo paths. You see, this effect here, it was related that there was not enough Monte Carlo samples in the simulation. Now I increase number of paths, then I see that the convergence was improved. And of course, higher the volatility you will use in a Oosterlee model. This means larger number of Monte Carlo paths you need to have, because you need to still get the convergence of that integral. Okay, so now let's do, for example, and that's typically 0.02. That's a rather large parameter for a short rate model. So typically it's 10 to minus 3, 10 to minus 4, or maybe even lower. This is 10 to minus 2. That's considered to be very big. Let me do, for example, like this. You see, spot on again. If we play with interest rates, so this will be 7% per year. Let me get even 10%. So you see, whatever I will choose change sigma, change interest rate, there is always perfect match between yield as an input and yield as the output. And that's crucial in those models under the HJM framework. Of course, now we still have a flexibility. So here we can choose the sigma, we can calibrate this model to swaptions, for example. Swaptions will be, it's an interest rate product that will be discussed in the follow-up lectures. But you can see that we don't need to care that our model needs to be calibrated to yield curve, because that's taking place by definition. So we only need to concentrate on calibrating the model to relevant products that we would like to price. This is also related to the, we have a picture a few slides ago when we talk about the Ferrari. You see here we have a Ferrari, because here we can calibrate. We don't need to calibrate the model. It's directly, we have perfect calibration for to the yield curve for free, essentially, by construction. So if we would have this equilibrium model, we would need to choose, we need to search for this theta function, time-dependent function, such that we have a perfect calibration, or we have a good calibration to yield curve. And that very often is not the case in those Ferrari models, let's say. This is always satisfied, and that's really great advantage of these models. When we talk about short rate models, I think everyone thinks of the full white model. The full white model, of course, is also belongs to the HJM framework. And interestingly, it's also, we can get this model, we can derive this model using the specification of the volatility under the HJM assumptions. So in this case, actually, we have it's not constant volatility for the instantaneous forward rate, but we have a constant volatility times decaying function. So you can see that at time t0, this number it's small, and then it's basically increases until it reaches 1. So in the, let's say in the long term, you can think you have a long-term volatility is sigma, and then we have some value which increases until this ultimate long-term sigma level. And the speed of how this function increases to the sigma is determined by the speed of mean reversion. So let's take a look. So we take this volatility for HJM, for the instantaneous forward rate, and again we substitute to the dynamics for the short rate model. So we substitute this volatility in all the terms that we have. So this is the definition, right? So we have seen it already before. This is again this derivative of the instantaneous forward rate, as we can see of today. So we can call it, we always call it a term structure. So we differentiate the term structure. We have alpha tt, and we have two integrals with respect to alpha and sigma. Of course, alpha under the risk neutral world is also defined as the sigma. So it's a sigma times integral of sigma. This is the arbitrage free assumption of the HJM framework. Okay, so if we substitute for alpha, because alpha is ingredient everywhere here, so we have this volatility, which is here, and then we times the integral, this is from s to t, over the volatility, and this is, of course, a closed form, nice expression for alpha. And also alpha tt is 0. I think this is, we already have discussed that before. We need to calculate the integral of alpha. So, but this is here you can see this derivative, partial derivative, and then we have integration. This is also known in closed form, and we also know the derivative of sigma, which is actually necessary in this element here. So we know this derivative of sigma, and it's also in this form. If we substitute all those ingredients into the dynamics for the short rate, we end up with a little bit slightly simplified form. We have, again, the differentiation of the term structure with a function of alpha, and we have two elements with a Brownian motion under Q measure. Interestingly, now I would like to address this one. So integral of sigma t dw s. And this one can be actually, if we look at the definition of the short rate under the HJM, this generic framework, we can actually see that this is exactly the same term as we know, as we see it for the dynamics of the HJM, so of the short rate under HJM. So basically we can substitute, so we know that this will be equal essentially RT minus F0t, and then we have integral of alpha. So after substitution, we end up with this dynamics of the short rate. There's a little bit of algebraic expressions. You have to be fluent in substitutions, essentially, and not so much more, maybe integrals and derivatives. And once you specify volatility for the instantaneous forward rate, you can basically just evaluate formula for the short rate. And this formula for the short rate always will be a function of the instantaneous forward rates. This is the key element of the HJM framework. So in this dynamics for the short rate, we see there is a lambda, here mean reversion. This is time-dependent function given in terms of market instruments. This is the same, just not derivative. And here we have the function, which is also in terms of model parameters. This is our RT, so this is the same as here. And we have a volatility. So volatility for underhood white, of course, is just a sigma dwq. So what we can do, we can substitute everything here because this is just a time-dependent function. It's not stochastic, and express it as a function theta t. And this is what we arrive. So theta t after that substitution, and then we end up with a famous whole white formula. And again, this, as we have seen it already in Oosterlee model, the theta t function guarantees the construction from HJM for the theta t function guarantees that the zero coupon bonds obtained by integrating short rate, taking exponent and taking expectation of that the zero coupon bonds, as we use them as input, would be also guaranteed as the output. And then what we have left, we have two parameters. So now we have two parameters compared to Oosterlee model because we can choose volatility and we also can choose lambda in order to calibrate. Also, we have this initial, but also I have described here below, this initial for Oosterlee white model has to be linked to the yield curve. So we have to make this epsilon close to today, and then we just estimate. So, and this is also kind of important. So if you forget about this R0 or you just choose it to 0, then you won't get any more arbitrage free. You won't get your yield curve back. So this is also very important that you always make sure that your R0, it is not 0, it is actually equal to the implied from a curve. And then you have two parameters with lambda and sigma that we can use to calibrate. In practice, typically a lambda parameter would be fixed or recalibrated on a rather monthly or weekly basis. The sigma parameter would be calibrated on a frequent basis to using swaptions or caps, depending on what type of product we are interested in the price. In practice, once we talk about calibration, you should always calibrate your model to instruments that are going to be used for hedging. So, for example, if you have a payoff, let's say in terms of, let's say, stock options, if you have American option, but you are calibrating your model to something completely different, or you are not using European options because that will be normal hedging instruments, then you'll be always off. So always use only the instruments, or you should not, maybe illustratively, if I have maturity contract of 5 years, it doesn't make sense to calibrate my model to 20 years because 20-year instrument will never be used or unexpected to be used as the hedging for 5 years. So your scope of hedging instruments should be always limited to what exactly calibration instruments should be limited or determined by the instruments that you're going to use in your pricing and also hedging. So if you have instrument which expires in 5 years, you should not calibrate to 20 years because there is no really point of doing that, because there is more important that you'll be using short-term instruments for hedging purposes. So here typically lambda will be fixed or recalibrated on some infrequent basis, and we have a volatility, which often can be also expanded to sigma to be time dependent, because this is typically the flexibility we need, especially if we talk about term structure volatilities, because theta function will not give you term structure volatilities, will only give you a yield curve. So this is a yield curve YC, and here we have a volatility term structure. So then we need to have time-dependent volatilities. In the full white model, it's a very similar structure as we have seen maybe for CIR, but there is no limit on the zero. So we don't floor it. It's always, it can be negative too. Full white model has a normal distribution. In next block, we will derive this distribution. But here you can see, again, we have a long-term mean. Here's 5%. And depending on speed of mean reversion, like a lambda here 5, it's a fast mean reverting. Red curve, it's a lower mean reversion. And even if we have negative or close to 0, then it's slowly mean reverting. And this is impact of the volatility. More volatility we have, more oscillations, but more uncertainty we introduce to the model. Let's take a look at the code. This is a code for simulating of Monte Carlo. Maybe not the most exciting code, because we already have seen it for Oosterlee, etc. But here I would like to just stress the simulation of the theta t function. So this is important that your theta t function, it is here I defined as a lambda expression. So for every time t, we have to differentiate. You can see here, we differentiate instantaneous forward rates. And those are calculated using, you see another lambda expression when I take logarithm of a zero coupon bond. So zero coupon bond, your yield curve is an input, then you define your instantaneous forward rate, and then for theta, you differentiate it. Of course, there are also ways how to simplify it, how to make it faster, how to make it more efficient in terms that there is less differentiation. So there are a lot of possibilities how to improve this implementation. But here I really want to focus on not maybe efficiency, but on illustration, that you can really see what is the input, what is the output. Of course, this code is not used for production, it is only for educational purposes. And here we see we don't have any more flooring as we had for the for CIR process. So here we just do Euler discretization, and we have volatility. Actually, I call it eta here, but in the slides was sigma. And if we just run it, we see this impact of different mean reversion parameters and volatilities on your paths. Yes, actually, this is nice graph, because you can see this is really actually going, looks like it goes like a stock, right? So exponentially. Of course, if I change seed, that won't be the case anymore. So let me change seed for both of those graphs. You see, it is not anymore. So sometimes you have a single path which behaves really unexpectedly, but once you simulate more and more paths, there is a more pattern you have about mean reversions. So again, here, fast mean reverting goes really fast to the mean. Slower mean reversion is orange line. We have a blue line which goes very, very slow. In the next step, similar as we have done for Oosterlee model, we will define market zero coupon bonds in terms of R minus TT. Of course, like I mentioned before, you can make it this function as you wish. Of course, it has to satisfy a more realistic the function, of course, better results you will have. If you put here sinus or cosinus, I'm not sure whether the results will be very realistic. And we do what we have done before. We will simulate Monte Carlo paths. We will estimate the expectation from based on the integral of from the short rate, and we will compare market yield curve compared to the one obtained from full white model. This is what we all have seen before. So we need to have initial, which is based also on the yield curve, and something still important, that we have two parameters now compared to Oosterlee. So we have much more flexibility once we talk about the calibration to some exotic derivatives. And now we go to the Python experiment. So let's take a look. In Python code, we generate Monte Carlo paths. So this is as we have done it already before for the Oosterlee model, and also for paths from full white model. So this is just discussed a few seconds ago. And here what we do, we generate the paths and calculate in this code here, we calculate expectation of 1 over mt. And you see that t is actually here is an index. It is running in time, and we take the expectation, and this will be equivalent with the expectation of the integral minus so it's expectation of an exponent minus integral of a short rate. So it's basically 1 over m is equivalent with 1 over m. It is expectation of 1 over m is equivalent with zero coupon bond. This is the proper way to stress that. And then we compare those values. So let me run the code. you see again is perfectly fit. So we can also now we can change parameters. We can make a mean reversion, let's say 10%. You see there is no impact, 20%, no impact whatsoever on the yield curve. So we have now if I change the volatility, let's make 2 here. You see maybe there is a small deterioration in the quality. This could be related to a larger volatility with more Monte Carlo paths. But if I think increase number of Monte Carlo paths, this would be also better. So again, we have 2 degrees freedom. So we have 2 parameters that we can use to calibrate, and your model, the model of full white, will be ensured that will be ensuring us, making sure that the yield curve is always perfectly calibrated. And this is the most important takeaway from the short rate models under the HJM framework. And also every model under HJM framework, the yield curve is an input, and model will generate by decision, by the construction, model will generate yield curve as it will ensure that the model fits the market almost perfectly. This is by the construction. Of course, in practice, you may have, if you have definition here of the zero coupon bond curve, and you have only few market data points, then you need to define also some kind of interpolation. And the question is how you choose this interpolation and how this will affect your outputs. So there's a lot of, let's say, practical discussions on how to choose interpolation between zero coupon bonds. But this is outside of the scope. Here, I would say just if you have a yield curve and it's time dependent and it's continuous, so you make sure that your interpolation generates the continuous values that also differentiable, so you can differentiate to calculate the theta t function, or actually we need to do it twice. So it's twice the differentiable function. Then you can just simply plug it into the full white model, and the full white model by construction will ensure that your yield curve is always fully recovered and will fully replicate your inputs. So then you have those extra degrees of freedom you can use for calibration. Later we'll be discussing in this course pricing of swaptions and others. So then we can use these extra free parameters to calibrate the market to really price derivatives. Otherwise, we would not have this extra degree of freedom. So this is a Ferrari in a short rate in the interest rate world, especially if you compare to the equilibrium models where we don't have those extra degrees of freedom to calibrate the model. Now is the time to summarize what we have learned in today's lecture. This lecture consists of 2 blocks. In the first block, we covered 3 topics, important topics. We discussed equilibrium models and term structure models. The most important takeaway here is whether yield curve is an input or it's an output. And then we talked about the HJM model assumptions. So those are the very important, this is very important framework for modeling of interest rates. And I hope that now it's clear to you what are the specifications you have to think of if you think about arbitrage free conditions in the interest rate world. And this is basically also the topic which was covered here. In the second block, we discussed particular choices of volatility for the forward rate under the HJM framework, so the instantaneous forward rate, which defines the interest rate dynamics. For that, we can specify different volatility coefficients, and that would give us different interest rate models. So by changing the volatility, we could, for example, arrive at Oosterlee model or full white model, and those 2 were discussed in this course. And of course, as you have seen, we have done quite some simulations in which we compare yield curve, for example, as an input, and compare from the output from the model. Now is the time to summarize, and of course the most important is the homework. I have prepared 3 exercises. The first exercise is about the exponential Vasicek model. So we have a mean reverting Olmsted-Umbeck process for y. So this is just you can think of Vasicek model, and then we take an exponent of y. So this process is you can see this approach here of defining the exponent of a rate was in the past introduced in order to address the problem of negative interest rates. So you see that in order to make sure that the rates are always positive, the idea was to take an exponent, then we make sure that interest rate under generated from R are always non-negative, positive in this case. For this exercise, we will continue the next exercise, but there are a few things that I would like you to check. The first is to apply Ito formula to RT and show that the dynamics for exponential Vasicek is of this form. And then you also have to calculate the expectation and check the limit, how this long-term short rate behaves as a function of parameters. In second exercise, so this is something about the hedging. We have, again, Vasicek model. I made it very simple so that you don't need to care about the yield curve. So we have constant function, constant parameter theta. We have some model parameters. And what we are considering hedging of a bond. So we have a bond, which is a 10-year bond here. And then we are looking for weights, W1 or omega-1, omega-2, and such that the variance of the integral from 0 to 10 years, variances of these two are equal. So this is called minimum variance hedge. This means that uncertainties on the hedging instruments related to the other instrument, the variances, uncertainties are the same. So this is kind of nice experiment. You see that there is we have this also integral, so we have to integrate over time. So this quantity is also stochastic. It's not deterministic, of course. Inside, if you take expectation or variance, then it's just essentially a number. And you have to choose those weights, omega-1 and omega-2, such that they're equal to 1. And the reason here is that we would like to basically make sure that you have a little bit of bonds, PT1 and also PT2. So it's kind of a portfolio, how much money you would have to redistribute into different bonds. In bond C, you have to change the measure of this process and also measure the variance impact of measure change on the variance. In the final exercise for today, we still consider this exponential Vasicek, but in order to fix the problem that the rates can be actually negative, but we would like to still have our rates to be of exponential distribution or log normal distribution, let's say, then we would like to fix it by so-called shifting. So we introduce a parameter, you see it's a zeta, which is positive. So we are shifting all the paths from R by this amount. Your task is to, of course, to find the dynamics of this R tilde, simulate Monte Carlo paths, and compare it to R. So you have to compare these two models. And then also look at the impact of the zeta parameter on the zero coupon bonds. I think those three exercises are quite nice. So it allows you first to look a little bit on the theory on how to calculate Ito's dynamics, Ito's process for a given system of equations. You also calculate expectation, some limits. We have also mean variance hedge. So it's also something that we will discuss further in this course. And then we also address the problem of negative interest rates that's present currently in the market. And this kind of shifting that we do here, it is a market, it's an industry practice to introduce shift if you have a problem that your rates or your model assumes the rates to be always positive, but you have also negative rates, then you can also always, this is the simplest way to introduce this negativity in the model. I hope you enjoy it and see you next time.